So this is a preview of the adaboost algorithm. So we have a set of training data, x1, x2, x3, xn, and then yi, the labels. And for adaboost, each point in the data set is going to have a weight. Okay, initially all the points have the same weight, so the weights are set to 1 over n, where n is the number of points in our training data. And then what we're going to do is to apply a base learner. So basically it could be a decision stump or it could be a shallow decision tree to weighted versions of the training data. And after you have applied this model to the weighted training data, what you're gonna do is you're gonna increase the weights of misclassified examples. Okay. So basically, what is the algorithm doing? So you are training models on different versions of the data because different points are gonna have different weights. Okay. And after you do that, you change the weights and train another model. Okay, so all of these decision trees, for example, are gonna be trained in a slightly different versions of the training data. Okay, so this algorithm is very different than, say, random forest, because in random forest you always see the same data or the same version of the data. In here, we're changing the weights of every point. Okay. And finally, we combined all of these base models, these trees maybe, by weighted voting. So we also have to define how we weight each one of these trees. Okay, so we're gonna talk about that as well. Before we talk about that, let me show you some beautiful pictures I found online on how to explain this. So the original data has every point be weighted the same, okay? And you go and you apply your regular decision tree to that. For example, in this case, what happens is that we divide this data in x1 bigger than 0 or x1 smaller than 0. So we put a line that divides the data in two at x1 equals 0. Okay, so for x1 less than 0, we predict everybody to be -1, and for x1 bigger than 0, we predict everybody to be a +1, right? So that's what happens here in the first iteration of the data. Now the points, for example, let me kind of show you which points I'm talking about. So the points kind of here, these points here, these pluses here are getting misclassified. Also, these minuses here are getting misclassified. So what we're gonna see is that we're gonna increase the weights of these samples, these observations that get misclassified by this particular stump. Okay, so let's look at them now. So you see we went from this classifier to, do you see these minuses? This minus here, they are kind of have a bigger weight, and these three pluses here have a higher weight because this were the points that were misclassified by the algorithm. Okay, so then what we do is that we now apply another decision tree, but to this data. So what is going to happen is that you are going to put more weight. If you think about any loss function or any cost function, is a sum of weights on every point, right? So instead of summing everything with the same weight, we can sum things with different weights, and that's actually what we're going to be doing. Okay, so we're going to have a weighted loss function instead of a regular loss function, right? So we're going to weight these big pluses and minuses higher than the other points, okay? So, and by doing that, what happens now is that we divide, we have another decision stump that divides the space into these two parts, okay? Where basically everything in green gets to be a plus, and everything in purple gets to be a minus, okay? So after this happened, then we again reweight all of the examples. So, and then we keep going, yeah? But then if we stop here, we're gonna have two models, right? Each one of them are gonna have a slightly different weight, okay? So the first model is weighted 0.61, and the second model is weighted 0.53. And then our final model is the weighted average of these two, and it's gonna be this model here, this final model here, which is an ensemble model, okay? Now if we basically use a decision tree with the classification error, what we're trying to do is to find the splits in the data that will minimize the classification error, okay? So we're gonna find a feature and a threshold that will minimize the classification error. How would you generalize this to the case in which the errors are weighted? Basically, data is weighted, basically. Well, I mean, it's what we talked about before. So what we're going to do is basically, we're gonna sum the total weights of mistakes, and we're going to divide by the total weight of all the observations, okay? And so this, we have here this fancy notation I have here that basically says, so what is this here, guys? So remember that this is gonna be, so if you parse this equation here, this is gonna be 1 when the tree is misclassifying this example, okay? So what this kind of fancy notation is saying is I'm gonna add WI when this tree is going to misclassify my example, okay? And I'm gonna divide by the total of weights, okay? So basically, the top part here is the sum of weights that are misclassified by the examples. And that's gonna be my weighted classification error. So instead of using a regular classification error, I'm gonna use a weighted version for working with adaboost. So what I wanted to do now is for us to wait for a second here and make a look at this example, okay? I have an example here, and try to find the stump that minimizes the weighted classification error for this example, okay? And I think you guys should stop this video and try to do it on your own, but I'm going to also have a solution right after this. So let's put, it's actually, so we are working in 2 dimensions, right? So it's always useful to like make a little diagram here, right? And say, well, actually this is 0, this is like, 1, and this is 2. Okay, so maybe this is 0, and 1 and 2, 0, 1 and 2. Okay, so our first point is here and has a label +1. Our second point is, sorry, this is 1, this is 2. Our second point is here and has a label -1. And our third point is here and has a label +1. okay? So and at the beginning, all of them are gonna have, sorry for this, so at the beginning, all of them are gonna have the same weight. Sorry, in this case, all of them are gonna have the weights that I'm showing here. So the first point is gonna have weight 1/5. The second point is gonna have weight 3/5, and the third point is gonna have weight 2/5. Okay, so what are all the ways in which we can, let me put a red on the points themselves. So this is my point, this is my second point, and this is my other point. Okay, so we have 3 points. In how many ways we can separate these points, right? With one line parallel to the one of the axes, right? So let's consider some options here, right? And let's look at what is the best 3 based on those options, right? So the first option here is that I say, well, I am gonna separate point 1 from point 213. Okay, so the first question I have for you guys is that, so basically I have a 3 of x, and basically I'm saying, you know, I'm gonna do x1 less than 0.5 or x1 bigger or equal than 0.5 0.5. Okay, so what would be the best option for, say, x1 less than 0.5? Well, we just have one point here, which is the first point, right? And that point has a label +1. So the best thing would be to say, let's put a +1 for this one here, right? What about for x bigger than 0.5? What should be the prediction there? Well, we have 2 points, one with label -1 and one with label +1. But the one with label -1 has a higher weight, so has weight 3/5. So it looks to me that we should put a -1 here for this to work, okay? So that would be the best 3 that divides the data in this way on this training data, okay? So now, what is the classification error of this tree? So this tree is misclassifying the third example, okay? And that example has a error 2/5. So basically the only example is misclassified is the third one. It has 2/5 as an error. So I'm gonna do 2/5, which is the weight of that example, divided by the sum of all weights. What is the sum of all weights? So we have like 1/5 plus 3/5 plus 2/5, okay? And this is like 2/5 divided by 6/5, and this is equal to 1/3. Okay, so that would be the error of that particular tree. Okay, so now we have to figure out which other ways we can divide this data. Okay, so maybe let's I'm gonna leave it like this here, and let's make another diagram, maybe a better diagram. So we have the first point. The first point was here, the second point was here, and the third point was here. And the first point had label +1, -1, and +1. Okay, so in our first we split kind of the data in this way with x1 less than 0.5, I think kind of the only way, the other ways to divide this data is either divide it here, right, or divide it here, and they're gonna be pretty much similar to each other in the sense that they're dividing the space in a very similar way for this training data. So let's consider let's consider dividing the data kind of this way here. Okay, so let's consider the 3, let me actually show you the example, the 3tx now, that is basically saying I'm gonna divide the data in x2 bigger than, this is like 0, 1, so it's 1.5, okay, and x2 less or equal to 1.5, okay. So what is the best prediction you can think about for x2 bigger than 1.5? So it's this part here, right? And in here we just have one point in our training data, and that point has a +1, so that's kind of very easy. So we're just going to give a +1 prediction here. Now on the second part we have 2 examples, right? Again, we have this example here that has weight 3/5, right? We have the example here that has weight 3/5, and we have this guy here who has weight 2/5, right? So the 3/5 is higher, so we're going to give so the best way is just to give here a -1. Okay, does it make sense? So guys, what is the error of this 3? Okay, so this 3 is misclassifying example. Okay, so I'm thinking about this again. So I see. So this 3 is misclassifying example 3 again, right? So let me see. So here we gave, I see. So yeah, so this example is misclassifying. So in here we are misclassifying this guy here. So let me change to green. We are misclassifying this example, which is the first example and has weight 1/5, right? So now the error is going to be 1/5 divided by the same, by 6/5, okay? So this is 1/6, okay? So basically from the 2 trees that we constructed, that are the possible, from all the possible trees that we could think of, the one that minimizes the error is this 3 here, the second one we built. So our algorithm would pick that 3, okay? So I hope that this helps you understand how to choose weighted trees, okay? So make sure you understand how to write down this example. Let me know later if you have any issues with it. Okay, so that is good. So let me actually show you the actual algorithm, and again you're gonna see that there are a few equations here, and hopefully by now this is gonna be a little bit more less alien to you. So we initialize our weights. They get initialized uniformly, so to 1/n, okay? We feed a classifier to a weighted data, okay? In the kind of the way that we have described before, right? Basically just considering a weighted error instead of just kind of a regular error, okay? And then we compute the error of that 3. And you know, guys, remember this very fancy formula here, what it's doing is summing the weights of the misclassified examples and divide by the total weights. So it seems very complicated, but it's not, okay? Then we compute this value here, alpha, okay? So I'm going to talk about alpha m in a second, but that alpha m is going to be the weight that we're going to give to that particular tree, okay? And then we reweight every example, and I'm also going to show you what this is doing. And finally, after you have fitted m trees, then we're gonna sum all of them. We're gonna do a weighted sum, and the final classifier is gonna be the sign of that weighted sum. Okay. So hopefully this is similar to the pseudocode I showed you before. But now I am gonna go in some detail to these terms. What are these terms, error and the alpha m? What are they doing? Okay. So, and then the weights as well. So let's look into that. So I would like you guys to think about a few examples. Okay. So let's say that we have different classifiers, and we're trying to define this alpha. Remember, the alpha is going to be how much weight we give to a classifier, okay? So intuitively, what we want is that a classifier that has small error is going to have a large alpha, okay? So I would like you guys to go and compute the values of this alpha for different values of the error, okay? So for example, for 0.01, what we're going to compute is the log of 1 minus 0.01 divided by 0.01, okay? And the same for all the other values. So I will give you a minute to stop the video and to do that, and I am myself gonna compute these values as well. So for the first number, I am getting here 4.6, around 4.6. So I'll get here 4.6. Okay, let's compute it for the second number. So I am getting 1.38. Okay, and finally for 0.5, I will get a 0. So remember, like if you have an error of 0.5, you're not doing much, right? So basically you should get a 0, right? So you're not doing much. So basically, I don't know if I am convincing you that this alpha m kind of makes sense. So the higher your error is, the lower is gonna be this alpha. So you're gonna take that model less into account in your final summation, right? Because you're summing with the weight of alpha. So the more accurate this model is gonna be in terms of the weighted error, the higher is gonna be this alpha. Okay, so cool. So hopefully you guys, this is kind of useful for you to see. So now let's look at how data is reweighted. Okay, so this is the formula that I showed you before, and I just want you to see that this formula is basically, it's gonna be keeping the weight the same, okay, if the algorithm classified, the model classified this point in the right way. And it's going to be multiplying this weight by the exponential alpha m otherwise, okay? So now notice that, let's see, exponential E of alpha m. Remember that alpha m, it was a log, right? So it's E of the log of like 1 minus error divided by error, right, guys? So if you look at this here, right, so this is the formula. So actually this number there is gonna be equal to 1 minus error divided by error. Okay, so what happens if so if your algorithm is correct, the weight is always going to be the same. So it's going to be the same weight. Now, if your algorithm is incorrect, okay, you're going to look at the error and compute this number here, and you're going to multiply by that number. So you're going to do weight WI times this number here. So let's compute that number for different values of the error, okay? So for example, for 0.2, what happens is that this is gonna give me this is gonna give me 4. So for 0.2 is gonna give me 4. If I had a different value, so basically and this value here is gonna be always bigger than 1 if the error is smaller than 0.5. So you're always going to be multiplying the incorrectly classified observation by a number bigger than 1. Okay, so you're gonna give her more weight for the next algorithm to pick up that weight, okay, and to classify them in the right way, hopefully. Okay, so I hope that this notation is becoming more familiar, okay, and basically I just wanted to show you that if your algorithm is correct, you're gonna keep the same weight on that example. If your algorithm misclassified that example, then we're gonna multiply the weight by a number that is bigger than 1. Okay, so finally, I am gonna stop the video right here, but I'm gonna have another video in which I go through an example on how to run the whole gradient boosting, in this case adaboost, on a very small example. Okay, see you later.